Another very important concept to understand is the idea of process gain. When we have any type of process we're trying to control, there's actually several gains to consider, but one of the ones we'd want to look at is the process gain, and also the gain of the measurement device and the final control device, really from the perspective of the controller. You can see a diagram here with the controller, and let's think of some particular concrete example so that this can make some sense. Let's say that the process is your car, and you are the controller trying to control the speed of your car. Well, your final control device from your perspective is really the gas pedal, and then the measurement device is simply the speedometer on your dash that measures the speed of the process, which is your car. Of course, the process includes the engine and I guess the linkage from your pedal all the way to the engine and so forth. But the gain, the idea of the gain is that as the controller, what are you outputting? Well, you're outputting a change in the gas pedal position. Okay. And what's coming in? Well, it's a measurement of speed. You see the speed on the speedometer. Now, on a controller, in controllers in industry, they don't hardly ever work with the actual variable itself. So it's not like you would get in the speed of the car if you were to put a PID controller in place of you to control the gas pedal. Instead, what you would get is a percentage. So let's say your car can do 0 to 120 miles an hour, or let's make the math easy and say it's 0 to 200 miles an hour. That would be a fun car. So if it's 0 to 200 miles an hour and you're doing 50 miles an hour, then the input signal into your controller is a 25% signal, right? Because the car is going 25% of its maximum speed. On the other hand, if you're doing 200 miles an hour on the Autobahn, I suppose, or on a racetrack somewhere, that's a 100% signal coming into the controller. So the thing that comes into the controller is a percent signal, and what comes out of the controller is a percent signal. Now, how does that work? Because the output of the control, the control device is a pedal. So how do you decide? Well, the pedal could be all the way released or all the way to the floor, right? All the way released would be 0%. All the way to the floor would be 100%. Halfway in between would be 50%. So this idea of percentage brings with it a calibrated range, a range of operation that we don't intend to go past, or no, we cannot go past. So let's go back to more of an industrial example and talk about just simply flow. If we have flow in a pipe, there's a certain range that we plan to flow over, probably 0 gallons per minute, liters per minute, whatever we want to use. A flow of 0 is probably in there, right? Because most of the time we want to be able to stop the flow. It doesn't have to be, but most of the time it would be. And then whatever the maximum flow is, that would be our maximum. So let's take an example of a span of 200 liters per minute, from 0 all the way to 200 liters per minute as the maximum flow rate through a pipe. Well, if the measuring device is calibrated to give the controller a 0% signal at 0 liters per minute and 100% at 200 liters per minute, then we can start to talk about gain and understand what is meant by it. Because if the controller outputs, let's say, well, you can see the purple line there on the graph, it went from 20% to 30%. So that's a 10% increase. Now, what's the final control device? Well, it's a control valve that can be all the way open or all the way closed. So where the valve was open 20%, now we've opened it to 30%. Okay. Of course, it doesn't have to be that, but let's just pretend that's the case. In that case, if this is a valve that when you push the stem in, and so we push it from 20% to 30% in, the flow rate goes down, well, then obviously increasing the output of the controller decreases the flow coming back. So this is not a valve you push the stem in to open. This is a valve you push the stem in to close. So 100% signal ideally would be our 0 flow rate. Now let's just pretend that the flow went from roughly 55% to 50%, or well, it looks like more like 47.5%. So the flow decreased by 7.5% of its range. Now 7.5% of 200 liters per minute means that it dropped by 15 liters per minute. Notice I didn't specify the particular flow rate at the beginning or end, just the change in it. And that's really what controllers are all about. They're about changes in things. So you sense a change in a variable and you, as a response, change a control variable. So part of the gain, if you think about the gain, what is the gain? Well, gain is simply the change in the output over the change in the input. And so what the controller would have seen is the controller changed the output by 10%. and the input changed by 7.5%. So you just take the ratio, and that would be the gain. At least now we have to be careful here, because the controller itself has a gain, and if we're talking about the gain of the process and the field measurement device and all of those things, then it's the inverse. It would be the let me think about this. Let's see. Output is, what do we say, 10%? Yeah. So if if the result changed by 7.5%, then that would be an apparent input over output of 7.5% change, if that makes any sense. So each one of these devices, the point is, each one of these devices has a gain associated with it, and the ones we can really affect are the gain of the measurement device, sometimes the gain of the field control device, but always we can change the gain of the controller. And changing that gain is actually something that's really important, being able to set it to a right amount. Now, if you think about the parallel form of the equation, where we have Kp, Ki, and Kd as the process gains, if you want to change the gain of the controller overall, you have to change all three of those gains. But in the Honeywell form, or the ISA form, I think it's called, in that form you've got the proportional gain multiplied by a quantity that includes the error, the integral of error, and the derivative of error, with some TI/TD tuning parameters. And when you change Kp, the gain, you're changing the overall gain of the controller. And so that's why that controller equation, the Honeywell form, is preferred, because you can easily change the gain of the controller by just changing one number without having to retune your controller. Because you see, this idea of gain is how sensitive something is to changes. Something like a cruise ship would have very low gain. If you turn the wheel, it would barely start to move, right? Or turn. But if you turn take the wheel on a speedboat and crank it to one side, all of a sudden you're going to have a very rapid response. So it has a very high gain. It's very responsive. Maybe acceleration would be a better example for that. Now, if the technician changes the measurement range of our measurement device, so that instead of 0 to 100% corresponding to 0 to 200 liters per minute of flow, if instead now it corresponds to 0 to 150 liters per minute of flow, and we make an output change from the controller of 10%, we would view a larger change, because remember, we're still essentially affecting the physical valve by the same amount. The stem has moved the same amount, and therefore the process is going to respond with the same change in flow rate of 15 liters per minute. But 15 liters per minute of a range of 150 liters per minute that the process can achieve, apparently, because that's what the measuring device is set to, is a 10% gain. So here we would see a gain of input to output of 1 to 1, because a 10% change on the controller's output corresponds to a 10% change in the process, and the process as viewed from the measuring device. So this idea of gain is something you kind of have to get used to. It's important. It actually affects all of the devices, and it's the reason that it's one of the primary reasons that you got to retune a controller when you apply that controller to a different process. Different processes have different gains. They have different sensitivities to their control variables, and so you have to choose the right controller gain. In other words, you have to tune the controller to the process, the particular process. Now, unfortunately, the story's not quite that simple, because processes very often will not respond the same amount. It's kind of like if you were to, let's say that you have a kid and you buy the kid a toy. Okay, so you buy them one toy, you bring it home. They're all ecstatic and excited. Of course, I'm saying this because I have a daughter and I've experienced this. If I were to immediately after that give her another toy, she'd probably be excited, but not quite as excited as the first one. And if I then said, oh, surprise, I have a third toy, her responses would be diminishing over time, because I mean, one thing is exciting, sure, and maybe it would be wiser for me as a parent to wait a month or so, give her this other toy when the novelty of the other, the initial toy has worn off. But she has different process gains, and you see this around Christmas time. Kids sit down to open their toys. They eventually kind of get tired of opening toys, right? And they'd rather just play with the box that the toy came in. So in that way, processes will often have different responses to the same stimulus, if you will. So the controller might output an increase of 5% and the process variable goes from 65% down to 60%. Maybe the flow, let's make our lives easy and talk about a 0 to 100 liter per minute flow rate, or let's just go for 0 to 100 per minute, or 100 gallon per minute flow rate. So we go from 65 gallons per minute down to 60 gallons per minute. Okay, but then the controller goes from 25% up to 30%, same change, 5% change, but now we go from 60 gallons per minute down to about 52.5 gallons per minute, a change of 7.5 gallons per minute instead of the 5 gallons per minute from before. So then as we continue, you know, the controller just keeps stepping up by 5%, but the flow rate changes more drastically. It's a nonlinear thing. It's you know, the sensitivity of the process depends on exactly what range it's operating in. Your car is this way too, if you think about it. If you take your gas pedal, you'll notice that in the initial range of the gas pedal, the engine will tend to respond more rapidly. Or if as you get up to speed, right, the car doesn't respond as much. I can have my gas pedal at, you know, 95%. My car might be doing well. My car is not the fastest car on the block. I prefer efficiency. Let's just make up some numbers. So let's say that I go from 50% to 55% and I get an increase of 10 miles an hour. But if I go from 95% to 100%, I get a much smaller increase, maybe a couple miles per hour or so, because the engine simply can't really give me that much more. I might be dumping more fuel in, but the wind resistance is nonlinear, and so the car simply does not respond the same way with as much change in speed due to the change in the control variable. Now that's kind of the opposite of what I've shown here, where the process is actually more sensitive to changes in the higher output ranges. But obviously control valves are nonlinear often, and depending on what type you have, especially a ball valve. If you've ever dealt with a ball valve is just like it sounds, it's a ball. It's got a hole in it, and usually have a right angle handle on it if you're talking about a hand valve. And what you'll find with a ball valve is they're made to be either open or closed. They're not really made to control flow, although there are some special shapes in the holes through ball valves, triangle shapes and others, that can give you whatever characteristics you want of flow versus handle position. But your typical ball valve, by the time you crack the valve from 90 degrees to about 10 or 20 degrees, you've got full flow. There's hardly any resistance to flow, and so it's very nonlinear. And so the farther you turn that valve, opening it up further and further, analogous to increasing the control variable, you get very little change in the process variable, which is the flow rate through it. Now, to take care of this problem, adaptive control or gain scheduling is very common, where the controller senses whatever variable is important, whether it's the actual output or some variable that affects the gains, affects the process in some significant way. And you can have the controller gains change as a function of this other variable. And that way the controller can still give good control over the entire range of the process variable.